Alright, welcome back to Inorganic TUTOR'S Institute. In today's tutorial, we are basically going to solve two problems in Advanced Calculus 1, right? We are just trying to solve a problem, We will come back to structure the Advanced Calculus course on the channel for easy understanding and for people to easily accumulate concepts that are very complex in an easy way. Inorganic TUTOR'S Institute, our vision is to develop a world-class educational institute that integrates STEM programs and other business programs into a unified environment for the modern students. Okay, so this is what we are coming to solve. This is our first problem, basically two problems, all right? And one is under limits and the other one too is a limit problem, but it's kind of application, right? So our first problem is we want to use different part approach to show that this particular limit is equal to 0. And then when we are done using the limit of different part approach, we'll use the epsilon delta definition to verify our solution. Okay, so let's begin the process. As usual, if you want to know or you want to use the different part approach to solve a particular limit, then you know that first of all, you can use for the okay, so we are going to start with the different part approach to show that this particular limit is equal to 0, right? So, this limit looks cumbersome. It looks complex, right? So, we want to make it a very simple one for us to be able to use the different part approach on this particular expression, right? So, let's say that we are going to make this expression a very simple one for our own good, right? So let's write the problem. Limits as x, y approaches 0, 1 of x squared y minus 1 all squared divided by x squared plus y minus 1 all squared. We want to prove that this particular limit is equal to 0, right? And first of all, we are using the different parts approach. Okay, so I said let's change the origin or the system of the limit to a very simple one for us to be able to deal with it, right? So I'm saying that let u equals x, all right? And also let v equals y minus 1, right? Y minus 1, right? I'm trying to use a variable to represent the cumbersome expressions, right? However you call it, so that we can have a simplified expression to work with it. So we're going to have limit as xy approaches 0 and 1. Now our x here is u. We are representing that by u. So we have u squared into brackets y minus 1 now is v, right? So we have v all squared divided by x now is u. So we have u squared plus y minus 1 is v. So we have v squared, right? Let's forget about the 0 aspect. You know that, of course, we are taking the left hand side to prove and make sure that we have 0. Okay, so this can be simplified to u squared v squared divided by u squared plus v squared, right? So we have this now. You see, now this expression is quite simpler than having something of this sort, right? So now, as we have that, let's say that we have j of u and v. Because we change the x and y to u and v, we try to change this part to u and v as well, right? So we have u and v equals u squared v squared divided by u squared plus v squared. All right, so it's basically we are trying to denote all this by j of u and v, right? So now we want to show that this particular limit is 0. All right, we want to show that this particular limit is 0. What do we do? Step 2. In order for us to build a very confident and a very easy way for the basic ones to also understand, let's try to use what we called the different part approach to handle this before we use the epsilon delta definition. Okay, so as we said from the beginning, let u equal 0. We already know that our u is x, remember, so don't be confused. So let u equal 0. You know that the different part approach, or let's try to write that so that you don't get confused. So in order to boost our confidence, let's use the different part. Let's use the different parts to check. Let's use the different part to check. So first of all, we are letting u represent 0, right? So if u is 0, so let u equal 0. If u is 0, that means that x is what? 0, as we stated from the beginning. So that is x is what? 0. All right, and now we let v also represent 0. If v is 0, then in other words, we are trying to say that v is y is equal to 1, right? So let's also v equals 0, and that means that our y is 1, right? I believe you are cool with that. This is the basic steps so that you don't get confused. All right, so once we have that, then let's v equals mu. Let v equals mu, right? We are representing v by mu. That is a different part approach, right? So, you know, this is a straight line through the origin. A straight line through the origin. So that is why we have that. This is basically a straight line through the origin. So we're going to have j of u, comma, mv equals Now we have u squared into brackets. We are saying that v should be what? Mu, right? So we have mu squared divided by u squared plus our v is mu, right? So mu all squared. Remember, I said v equals mu is a straight line, right? It's a straight line through the origin. Okay, so here we simplify this to have u squared times m squared times u squared, right? When you expand this, you have that all over u squared plus m squared u squared. And you know that you have u squared here, you have u squared here. Indices said when you have the same basis and they are multiplying, you add the exponent. So you have 2 plus 2, and that is u to the power 4 m squared divided by u squared plus m squared v squared. Right, very beautiful one, of course. So this is what we have. So this is when v is equal to what? Mu. That is a straight line through the origin. Right. So once you get this concept, then the rest is going to be very easy, right? Because this is the different parts approach. Now we have to test every point. So every tested point, every tested part will give us 0, right? Every tested part will give us 0, right? So if we say that this should be 0, right? If you say that this should be 0, which is the u, then you have this part goes to 0, and you know that if this part goes to 0, then basically we have 0 over 0 plus m squared v squared. And remember, v is 1, right? So, and this is a constant as usual. So you have 0 over something, and that is what? 0. So if you test the parts along any of the variables, you get what? 0. I believe you are fine with that. If you have u equals 0, it means that the numerator will be automatically 0, right? And you know that 0 over anything is 0, right? So every tested part gives 0. Every tested part will produce the value 0. So this is strongly suggesting that the limit is basically 0. So every tested part gives 0, right? So this strongly suggests that the limit, right? The limit is basically what? 0. Okay, so this should tell you that the limit is 0. This is very simple, right? Very, very simple. So this is the choosing part, or the different part approach. Okay, now let's try to use the identity. The other step, let's try to use the identity to handle this. Now we have used the different part approach to basically tell the limit to be 0, right? We have used a different approach, different part approach to say that the limit is actually 0 as given here. So now let's come back and use the identity approach. Let's use the identity approach. So let me take off this as well. Let me take off this as well. Okay, so we are going to use the identity approach, or yes, the identity, right? So let's say that, let me rewrite the problem, the function again. Limit x, y approaches 0 and 1, right? X squared y minus 1 all squared, x squared plus y minus 1 all squared. Remember, when we're using the different part approach, we try to represent the x and the y by v. So as usual, we know that our x is u, our y is our v. Our v is equal to y minus 1. So when we did that, we have u squared v squared divided by u squared plus v squared. Right, so this is what we have as usual from the beginning. So using the identity, we know that u squared minus v squared all squared must be greater or less, must be greater or equal to 0. This is the identity. If you square the u minus the square of the v, the result that you have, it must be greater or equal to 0. So that is the identity. All right, that is the identity. So you realize that when you expand this, you're going to have, this implies that you have 4 u squared v squared less or equal to v squared plus v squared all squared, right? And this is denoting something, right? Now let's proceed. So we have 0 less or equal to u squared v squared, right, divided by u squared plus v squared less or equal to u squared plus v squared all squared divided by u squared plus v squared. Right, so basically this is, there is 4 here. So you know, yes, so that is it. So basically when you do this, you're going to have, and this is equal to u squared plus v squared divided by 4. Right, so this is the identity, right? This is the beginning of the identity approach, right? So you do this, when you expand this, you have that, right? You know, when you try to change the sign, you have to change the inequality sign as well. So that is what we have here. Now, you know that if you see you have this, let's assume that let's say that r squared is equal to u squared plus v squared, right? Now, then we can say that 0 less than or equal to j of u and v is less or equal to r squared over 4. So we represent this by r squared, right? And so we are saying that 0 less or equal to j of u and v should be less or equal to r squared over 4 from here, right? So now as u and v approaches 0, 0, as u and v approaches 0, 0, then we know that r squared will also approach 0, 0, right? As u and v approaches 0, 0, you know that r squared will also approach 0, 0, right? Because if you put 0 here, you're going to have 0. Okay, so this should tell you that the limit is actually 0 if you use the identity. So that is the limit is 0. All right, I believe you get this right. So far we have used the different parts, we have used the identity, and now we are going to use the epsilon delta definition, right? We are going to use the epsilon delta definition. So remember, if you want to use the epsilon delta definition, you have to check the structure of the problem before you start the process, right? You know, if you want to use the epsilon delta definition, we have 2 or 3 approaches, right? Where you have, where you can define the variables very easily. That is the direct substitution. And then we have the squeeze-based approach. That is where it is kind of difficult to, deal with the expression, right? So you try to use the squeeze-based approach, right? You write the expression in a squeeze-based form. 2 functions on the left and right, 1 function in the middle. So we assume that if the left and right functions are the same, then the middle function will also be the same. That is the squeeze approach. So let's come back to, now we have used the different part approach to basically show that this limit is 0, as you saw. Now we are coming to use the epsilon delta definition to also show that. But remember, as I said earlier, the epsilon delta definition, you have to look at the problem before you actually use it, because sometimes the direct substitution doesn't work. In this problem, we can't use the direct substitution, looking at the nature of the problem. So we have to use the squeeze-based approach, right? So let's use that. So we know that we have the function, right? So let's assume that the function is there. We don't need to write it here again. So with the epsilon delta definition, with the epsilon delta definition, yes, so it says that we should verify. So with the epsilon delta definition, with the epsilon delta verification, with the epsilon delta verification, we want to show that for every epsilon, it should be positive. That definition holds everywhere. For every epsilon, it must be positive. It must be positive. That is greater than 0. All right. And if it is positive, then it means there exists a particular delta that is also what? Positive. So let's try to define that. For every epsilon, it must be what? Positive. That means there exists delta, right? There exists delta that is also positive, right? And if this delta exists that is also positive, then such that, you know, as I said earlier, we are going to use the squeeze-based approach where you have a function here. Let's say you have a function, say g of x less or equal to a function of x, a function of h, right? This is the squeeze-based approach. You have one guy here, you have another guy here, there is one guy in the middle. How do you know the limit of this particular guy in the middle? So the squeeze theorem says that if you find the limit of this guy and you find the limit of this guy and the results are the same, then we must assume that the limits of this guy will be equal to these two guys, right? Since their limits are the same. But if you find this guy and it's different, you find this guy and it's different, then you can't determine for this, right? So for the squeeze theorem to hold, this guy and this guy must be the same. They must be the same. Then you can equally say that this one too is the same as these two guys' results. I believe this is good. All right, so we go with that squeeze-based approach because we can't use the direct substitution in here. So we say that 0 less or equal to, remember, we defined from the beginning, we defined x to be u, then to be y minus what? 1. So we're going to have u squared, v squared, divided by u squared plus v squared. Remember, this should be less than epsilon, right? So for every epsilon greater than 0, there exists delta that is also greater than 0, such that this definition is less than epsilon, right? And this will only hold whenever you have the square root of u squared plus v squared to be less than delta. So when you come to the direct substitution, you'll not be having anything like this. You'll be having an expression, simple expression for this, right? So we have defined our limits. So as I always say, this pre-definition, you are trying to define what this will be or what this is actually mean. So for instance, if you go to your office and your boss give you some work or something, you are to report. You write a preview, right, before you start to give whatever you want to give out to your boss so that he or she will understand the terms, the terminologies in the work. So the same thing applies to mathematics, right? So we're going to say that from the inequality above, from this inequality, we are going to say that u squared v squared divided by u squared plus v squared should be less than or equal to v squared, u squared plus v squared divided by 4. Now, if the square root of u squared plus v squared is less than delta, then we can say that u squared plus v squared is less than the square of this. You know that it is square on both sides, this cancels this, and you have this, right? Now, then we can have hence u squared plus v squared divided by u squared plus v squared is less or equal to delta squared divided by 4. Right. So I'm actually basing on the identity that I used in the right after the different part approach. I'm trying to use that identity in here, right? So to make this expression, to be less than epsilon, we have to surface it, right? So to choose that delta with something that is very, very small, right? So you have to surface it to choose that delta, right? So we're going to have delta divided by 4 to be less than epsilon, right? So this expression here should be less than epsilon, right? So what do we have to do? So this basically telling us that delta is less than 2 times of what? Square root of epsilon. You know why? When you send this here, you're going to get what? 4 times what? Epsilon. So you have delta squared less than 4 times what? Epsilon. So this should tell you that when you take square root on both sides, you're going to have square root here, so you have delta to be less than, square root of 4 is 2, so you have 2 times square root of epsilon, right? So that is for delta. Okay, so let's try to pick a very small number, a minimum number that will make sure that it works within the definition, right? So we are going to pick delta to be a minimum of 1 and then this value, right? So we're going to have our delta to be equal to a minimum of 1 and also this particular value, right? So 2 times the square root of epsilon, right? So that would be our delta, right? Now remember using 1 is basically optional, just to keep delta very, very small, right? We are using delta 1 just to keep delta to be very small value. So hence this completes the epsilon delta verification proof. Hence proven. Hence proven. Right? So this is the results. This is quite confusing, right? You'll be fine. Just make sure that you go through from the different part approach, come to the identity, try to understand the identity, then you come to the epsilon delta definition verification. You know, when it comes to this delta definition verification, when you have a problem that is a direct substitution problem, then it becomes easy for you to penetrate. But when it comes to an expression, a cumbersome expression, that is when you have to use the squeeze-based theorem so that can be able to manipulate the expression. So that is why we use the squeeze-based theorem to, deal with this guy. So our delta should be a minimum of 1 and also 2 times the square root of what? Epsilon. Hence proven. This is beautiful, right? Okay, give me some short minutes. I'll be back with question number 2. All right. Welcome back from the short break. I believe you have been able to digest the very first problem and you're good with it. You know, the limit problem. It was very interesting, right? Good. Now, this is the second problem, and that is where we are going to end for the day. This is the second problem, and it says that the area of a circular disc. So you have to take notice of this. It's a keyword of radius r centimeters, right? Is this. So it means that this is the area, right? Good. Now, a mechanist is required to manufacture a metal disc having area 400 pi centimeters squared, right? So this is the required area for the mechanic to manufacture a metal disc. This is the required area, right? And the circular disc has an area of this. Good. Now, within an error tolerance of plus or minus 5 centimeters squared. So they want to manufacture a metal disc having an area of 400 pi centimeters squared within an error tolerance. You know, when we talk about error tolerance, we are trying to minimize the problems, the challenges, the errors, right? So we are trying to the accepted or the acceptable error shouldn't exceed plus or minus 5 centimeters squared. It should be within plus or minus 5 centimeters squared. Now, we want to know how close to 20 centimeters must the mechanist control the radius of the disc to a circle to achieve this. Let's take the problem again. The area of a circular disc of radius r centimeters is this. So this is the area for the circular disc. And the mechanist is required to manufacture a metal disc having area of this within an error tolerance of plus or minus 5 centimeters squared. Now, we want to know how close, okay, how close to 20 centimeters to 20 centimeters must the mechanics control the radius of the disk to achieve this particular dream. Now, I want you to read the question over again and digest the problem. Understand it, right? So, let me give you the understanding from here. You also try to give your understanding and try to understand the mathematical terminologies within the problem. So, the record area was given as 400 pi centimeters squared, right? Now, you know that we're given some acceptable error, right? And that is plus or minus 5 centimeters squared, right? Okay, so we want to know how close to 20 centimeters will the mechanics be able to achieve this result. So actually, I use two approaches in this particular problem, but in this, we are going to go by one approach. Maybe later I'll add up the other one. That is cool, right? Okay, so let's take this. Okay, so we know that the area of the circular disc, so this is your presentation, given that your area of the circular disc is pi r squared. Pi r squared. So the area of a circle is pi r squared, right? So that is basically area of a circle, right? Of a circle is equal to pi r squared. Okay, so this should be your presentation. Okay, now we want to the closed area or the area to be exactly 400 pi centimeters squared, right? So we want the area to be exactly 400 pi centimeters squared. So how are we going to do this? Let's write that first. So the area, I want it to be 400 pi centimeters squared. Okay, we want the area to be 400 pi centimeters squared according to the question. Right, so that will correspond to a radius, right? A radius of what? 20 centimeters as given in the problem. How close to 20 centimeters must the mechanics control the radius of the disc to achieve this? So this particular information must correspond to a radius of 20 centimeters. So this or that corresponds to the radius of 20 centimeters. Note. Okay, once we note this basic information, then we can go ahead. You know why we are saying that this should correspond to this 20 centimeters radius? It is because when you have pi into 20, we have been given the radius to be 20, right? So we substitute it into the area of the circle, which is pi r squared. So we have pi into 20 all squared, right? And that should correspond to that. Okay, that should correspond to that. It should be the same. It should be the same. So area of the record our disk is 400 pi centimeters squared, and the area of the circle is pi r squared, and we have been given a radius to be worked with, right, which is 20 centimeters. So that corresponds to 20 centimeters, and because when you take the r, which is the 20, substitute into the area of the circle and you simplify, you're going to have 400 pi centimeters squared, right? So this is equal to 400 pi centimeters squared, right? So you know that this is equal to 400 pi. Okay, so that is why I am saying that it corresponds. So basically it's telling us that the area that we were given, pi r squared, the area of the circle that we were given is the same as the area of the metal disc, right? And that was 400 pi. Remember, we were given the radius to be within 20 centimeters. The close 20, right? 20 centimeters. Okay. Now, remember that the mechanics, right? The mechanics is allowed to work within an allowed tolerance, right? Which is plus or minus 5 centimeters, right? Allowed tolerance of plus or minus 5 centimeters squared, right? So recall that the mechanics is allowed. The mechanic allows an error in area of only plus or minus 5 centimeters squared. So this statement is basically telling us that the actual area, okay, the actual area can be between 400 pi minus 5 and 400 pi plus 5 because of this condition, right? Because of this condition. So this means that the actual area must be between 400 pi minus 5 and 400 pi plus 5. Okay, so this should be the actual area. Now, we want to actually know how close or how much, okay, from the question, how close to 20 centimeters. Now the mechanics controls the radius of the disc to achieve this vision, right? So now we want to know how much radius can change without the area of the area going beyond the given range, right? Without the area going beyond the given range, right? So, or going outside that particular range, okay? So what we are going to do is that we are going to take the very small one, we compute the result, then we have the minimum value of the radius, then we take the largest one, then we compute the maximum radius, then we see what to do or what you have. So let's try to convert the allowed, let's convert the allowed area the allowed area error into allowed radius values, right? So we are trying to convert the allowed area error into allowed radius values, right? So we are going to have, so we want to basically try to we are going to try to start with the minimum value, which is the smallest value, right? So we are going to start with, and we are going to use the area of the circle, right? So we know that area of the circle is pi r squared. Okay, so we substitute the smallest allowed area into this. This is very brilliant, right? So we're going to have pi r squared, right, equals, so we have pi, this is pi r squared equals, we're given something, right? And that will be this, because we are substituting the smallest allowed area or error, right? So that will be 400 pi minus 5. We need the radius, so we divide here by pi, divide here by pi. So this takes off this, and we have r squared equals 400 pi divided by pi minus 5 over pi. This takes off this, and then we have r squared equals 400 minus 5 over pi. Remember, we need r, not r squared. So we take square root of this right hand side. But note that if you are taking a square root of a particular argument, you have plus or minus of that particular argument, right? But in this instance, we are going to take only the positive. You know why? Because of the radius. If you are talking about distance, you cannot have a zero, a negative distance, right? It's either you have no distance, that is 0, or you have more than 0. So always a distance is positive, greater than 0. A distance is positive, that is greater than 0. So we're going to have r equals square root of 400 minus 5 over pi. Square root of that, okay? So let's go this way. So we're going to have, when you simplify this, we're going to have r equals square root of 400 minus 5 over pi. And you know that when you compute this nicely using your calculator, you're going to have 19.960. Okay, so this is the value you have. So this represents the minimum radius. So 19.960, the minimum radius. Okay, now let's move on to the biggest or the largest allowed area, right? So we're going to say that A equals pi r squared, of which it is equal to 400 pi plus 5, which is the largest part. Okay, so we're going to have pi r squared equals 400 pi plus 5. Okay, we need r. Okay, we need r. So we divide here by pi, here by pi. Okay, so we move up here. We move up here, and then we have r squared equals 400 pi plus 5 divided by pi. So we have r squared equals when you distribute the denominator to each of the items at the numerator, you're going to have 400 pi divided by pi plus 5 over what? Pi. So this cancels this, and you have r squared equals 400 over 400 plus 5 over pi. Remember, we need r, not r squared. So we take square root on both sides. And square root, when you take the square root, the square sign will go. Okay, so we have square root of 400 plus 5 over pi. And this will give us, when you compute this nicely using your calculator, you're going to have 20.039. So this is the maximum radius. So this is the maximum radius, right? It should be in centimeters. This as well should be in centimeters. Okay, so now what does this tell us? This is basically telling us that the radius, okay, which is the question says that how close to 20 centimeters must the mechanics control the radius of the disc to achieve this. So we can say that hence, okay, so let's write the conclusion. Hence, the radius must stay between 19.960 centimeters, 19.960 centimeters, less or equal to r, less or equal to 20.039 centimeters. So the radius must stay within this range, okay? It must not go beyond. Okay, so conclusively, this is telling us that the mechanics has to keep the radius, okay? He has to keep the radius within plus or minus 0.039 centimeters, okay? You know why? When you take this, which is 20.039 centimeters minus 19.960 centimeters, you're going to have 0.039 centimeters. But remember, we're giving plus or minus, so you also have to write plus or minus, okay? So this means that the mechanics, right, must keep the radius, within plus or minus 0.039 centimeters or 0.0398 centimeters. So the mechanics must keep the radius within plus or minus 0.0398 centimeters. Okay, so that is the end of the work. Okay, I'm just trying to add this beautiful sentences. So that is plus or minus 0.04 centimeters. Okay, when you change this to two decimal places, you're going to have 0.04, you know, one comes here and then you have 0.04 centimeters. Okay, this is about 0.4 millimeter. Okay, 0.4 millimeter. Okay, 0.04 centimeters is about 0.4 millimeter. Okay, so we can now conclude, right? We can now conclude and say that Therefore, to keep, we quote the question, right? To keep the area, within plus or minus 5 centimeters squared, the radius must not change by more than, it must not change by more than 0.04 centimeters from 20. It must not change by 0.04 centimeters from 20 centimeters. So let's write if the, okay, so that is basically the solution to the mechanic problem. This is interesting, right? I believe you have been able to. So this is the end of the problem, and I will urge everyone to share to their friends. Try to subscribe. That is where the joy comes from. And remember, in Organic Tutors Institute, our vision is to develop a world-class educational institute that would integrate the STEM programs and other business programs to a unified environment for the modern students. So please help us to build this dream to the highest level for the whole world to see this beautiful initiative. Thank you very much for watching. I really appreciate your time. See you next time. Bye bye.